All right, so let's look at this one. Find me the derivative of this one. There is a couple ways you can do the derivative for this one. So you can technically choose. They'll both come out to give the exact same answer. So. So if you did it as the product of multiplication or the product rule, you'd have gotten the same answer. I just distributed it, so I didn't have to deal with the product rule. And this one though, this is where when we had those conversations about when do you stop simplifying, and I said it really depends on what you're using it for. So on the last test, this probably would have been fine. Getting it to that point there wouldn't have been a problem. However, we now need more stuff. We now need to do stuff with this. So breaking it down to this, because I need a division to be able to find values that don't exist, I need it as one fraction to be able to do that easily. So by putting it together to be one fraction, I now can set my top equal to 0 and my bottom equal to 0 to be able to find those critical numbers. Where if it was set up like this, not as easy to find. Okay? So that being said, does everybody understand how I went from here to here? So remember, when you're looking for common denominators, the denominator and the bottom has to be the same. You can basically do cross multiplication to find the numerator. The 5's in both, so I didn't have to worry about the 5. So that's why the 12 stayed the same. So I didn't have to multiply it by 5. This, I'm just multiplying by the x to 2/5. X 3/5 times x to the 2/5. You add the numerators, comes out to be 1. So that's where the 8x came from. And the denominator is just the 5x. So we needed to get it back to one fraction to be able to work. Now we have to find our critical numbers. So we're looking for two sets of critical numbers, right? We're looking for when the problem equals 0 and when it does not exist. So if you have a fraction and we're looking for it equals to 0, what am I setting equal to 0? Just the numerator. So we're just going to do, this is a different color. We're going to do 12 minus 8x equals 0. So x equals 3/2. So that right there is one critical number. And that's when it equals 0. This one, I have division. So I can have a situation where it does not exist. And that would be when my denominator equals 0. So I set 5x to the 2/5 equal to 0. And the only way this equals to 0 is x equals 0. So I have two critical numbers for this one. I have x equals 3/2, and I have x equals 0. So now let's look at so actually, you know what? We're going to do another step before we do that one. All right, so we've got this problem. That's my original problem. We know my critical points were at 3/2 and 0. Before we do the graph, can we determine if those are mins or maxes? So to determine a min or max, we just need to figure out what the slope is doing before and after, right? Okay, so in this problem, we need to figure out, we need to set the numerator basically is when it's less than that point, when it's negative, and then we figure out when it's positive. Can the denominator ever be positive, or can the denominator ever be negative? Because when you're looking at it, that's going to make a difference. So if both the top and the bottom can be negative, then it makes it a little more complicated and different. Can this ever be negative? No, because we have x squared, right? So the fifth root could, but since I have x squared, that's automatically going to get rid of any negative. So the bottom will always be positive. Great. So since the bottom's always going to be positive, I just have to look at the numerator. So I want to know when 12 minus 8x is less than or equal, or not as less than or equal to, is less than 0. Because that's going to give me it to be negative, correct? So I kind of already actually solved this when I did the x equals 0. So I'm going to divide by a negative. So remember when we divide by negative, what happens to the inequality symbol? It flips. So this becomes greater than 3/2. So the derivative is negative, is less than 0 when x is greater than 3/2. So that means at that point, it's coming down afterwards. If I do the other direction, is greater than 0, I get x is less than 3/2. So f prime of x is greater than 0 when x is less than 3/2. So that means it is positive before that point. So that right there is a local max. It might be an absolute max, but I know at least that it's a local max. We also kind of know something about x equals 0. What do we know about x equals 0 now? I know that my derivative is always, my derivative is always positive when it's less than 3/2, right? So that means at 0, what's happening to the graph? if it's always positive, if the derivative is always positive at that point, it's going up to that point, right? It's increasing to that and increasing after. So is that a local min or a max? If it's increasing to increasing afterwards? No. Because remember, the local mins and maxes, it has to change direction. So because I showed this, I know that point, it's a critical number, but it's not a local min or a maximum. And since the slope or the derivative doesn't exist there, it's most likely going to be a vertical asymptote, which is what we're going to look at right now. So this is the original problem. All right. So there is my graph. And at x equals 3/2, that right there is most definitely, and that, in this case, we can zoom out some more just to make sure that it doesn't do anything crazy, but that's going to be my absolute maximum. And right here, if we zoom in, you can see that it basically makes a vertical asymptote at that point. Okay. So, but you also can see that the function is increasing going into it and increasing going after it. So my slope is still positive in those situations. So that's why it's not a minimum or a maximum. Okay. So we can start to use the derivative to start finding what's going on. All right. All right, your turn. Find my absolute minimum and maximum values of this function. We already did this function, actually. This is the one we already did. Oh, it added a couple other points. So it's fine. You guys can do that. You don't need to find your critical numbers because we already found them. But this one adds in one thing that we didn't do. It adds in the endpoints. Okay? So it adds in the -1/2 and the 4. So look at those because those could change your mins and maxes. I think those are already them all in my head. So all you're doing for this, you could have graphed it, but you're just plugging the values into the function. Let's figure out what the mins and maxes are. We already showed that 0 and 2 are going to give me a minimum or a maximum. So we didn't have to actually prove that using the derivatives to figure out which direction they were or looking at the graph. We already did that with the graph. So in this case, we're just really adding in the endpoints to see if those change. So now is an absolute max now a minimum, or I mean, an absolute max now a local maximum, things like that. So 0, 1 is a local max. It's not the highest point because there's one at 17. 4, 17 is the absolute max. Because this one kind of goes to infinity in both directions. So then we have 2, negative 3. That right there is now going to be a absolute min, because that's the smallest one. And negative 1/2, 1/8 is an endpoint, and that's not going to be that can't be a local minimum. So I have my local max, my absolute max, and my absolute minimum. All right. Let's actually look at where this is really used. Rocket science. So if anyone ever tells you, studying rocket science, yes, that's what calculus is. So the Hubble Space Telescope was sent up in 1990. It went up by the Space Shuttle Discovery. And this is the velocity of the shuttle from t equals 0 to t equals 126, which is when the solid booster rockets were jettisoned. Okay, so this is when basically the maximum acceleration out of the atmosphere at that point. So what they want to know is what is the absolute maximum and minimum values of acceleration. Why would we care? So yeah, that's going to be my acceleration, but what does acceleration directly relate to? Now we're going to see if you remember any physics class stuff. The faster you accelerate, think about a drag star or a race car. The faster you accelerate, what happens to your body? The g-forces. So the maximum acceleration will relate directly to the maximum g-forces that it's going to feel. The minimum will be the minimum g-forces that it's going to feel. Okay? So when you're trying to plan things out, yeah, the g-forces is what you care about. So really understanding where the maximum min is going to happen, they call it max q. That's literally the maximum g-forces that are on that load. So that's what we're looking at here. So when does that occur in the flight, and what is it? So to do that, we need to find what? What do we need to find to start finding our maxes and mins? Huh? Well, we do need, first thing we need to find is we don't have acceleration yet. We have velocity. So what's acceleration to velocity? That's your first derivative. Yes, so we have to find the first derivative of my velocity, and that'll give me my acceleration. So let's find the derivative of this. So acceleration of t is velocity prime of t. So we've got 0.003906 t squared minus 0.18058 t plus 2361. And my range is 0 to 126. All right, so that's my acceleration. Did I multiply right? I could just check. I could actually just check. Yeah. All right, so I've got my acceleration. Now what do I have to do? To find my critical numbers. Ignore the fact that this is a derivative. What do I do to find my critical numbers of any of the problems that we've done so far today? Well, I got to do what before I set it equal to 0? Ignore the fact that this is a derivative. So like the last problem. So actually 2 problems ago, because we did that one. This problem. What did we do first to find the critical numbers? Right. Well, we had to find the derivative. Okay? We had to take the derivative of the function to find it. All right? So the same thing we did with this one, right? Started it, we found the derivative. And then we did our critical numbers from the derivative, correct? Okay. There's a reason I kept saying ignore the fact that this is a derivative. Because we haven't done that step yet. Okay? Yes, we took the derivative of the velocity. But that was to find my acceleration. To find my critical numbers of my acceleration, I have to take my derivative of acceleration. Okay? So, which is kind of what you said before, you have to find the second derivative, because I needed to do the derivative twice in this situation. Okay, so I have to find the derivative of my acceleration. All right, so that is now my derivative of my acceleration. Now we're going to set this equal to 0. So I've got 0.007812 t equals 0.18058. So t equals 0.10858 divided by 0.007812, which comes out to be 23.12. And that's it. We have one number. All right, so what are the three numbers that I have to test? Yep, so we have to do 0. And if I plug 0 into that, I'm going to get 2361. We plug it back into the acceleration equation. And then we have to do the 2312. And then we have to do the 126. So the 2312 comes out to be 2152. Totally cheating because I did not do these out by hand. And 6287. Just plug the numbers back into acceleration. That's nothing crazy there. So those are my critical values and my two endpoints. So initial liftoff, and then at the end. So which is the minimum acceleration? When does minimum acceleration happen? Or when is the minimum amount of g-forces? Yep, 23.12 seconds. And that is 0.72 Gs. At 20, oh, sorry, I screwed that up. Hold on, wrong number. 52. 0.67 Gs, so 2/3 gravity. After 23.12 seconds. And actually, even at liftoff, it's actually having negative Gs. This 2361 is still negative Gs. Or not negative Gs, but it's less than Earth's gravity. So, all right, and then the maximum acceleration is at right at the end when the boosters come off. And that's 62.87. Which is 1.95 Gs, so almost 2 Gs. And that kind of makes sense because if you have maximum acceleration at the point when the boosters are going to break off, so it actually continues going, because at that point then the other engine that kicks in. No, there's the two solid boosters that pop up the sides, and I can't remember there's another one that's in the big tank in the middle from off the space shuttle. I can't remember what the name of it's called. Second, yeah. And then the space shuttle has its own run. Yeah. Works. All right, so that's why we need to actually start looking at this stuff. That's why this matters. Okay? And actually, even today, when you're starting to look at in sports, like football and things like that, with concussions and the helmets and everything else like that, they're looking at this type of stuff with collisions. It's like, where's the impact focused on and whatnot? And they're using calculus to do this stuff, to figure out how to actually make the helmets better. Same thing with NASCAR and racing and things like that. They're doing it with the cars to figure out where the highest impacts are, so that they can make the things safer for everybody playing. So, yeah. Mm-hmm. Yeah, because because that's where now in racing everything is like a Hans device and stuff to actually prevent the movement of the neck and stuff like that. I think you're probably going to start seeing some of that stuff in the helmet soon.
Now helmets are getting rounder and bulkier again. Other ones have to pass that test.
Yeah. So it's like it's all comes back to this.
This answers my question.
There you go. See, eventually we're going to get there. It's like sometimes, like in math, it's like you've got to get through all the basic stuff to actually see it, and then we can start applying it. Because if we sit there and just pull the application out in front, it's like you're not going to understand any of the math behind it. So it's like, okay, it makes no sense. So now you actually understand all the math behind it. So now that when we start talking about it, it's like it makes sense. So, all right. Royle's theorem. So Royle liked to make a name for himself. He hated calculus. He really did. And then he realized that there was a use for it. So he made a theorem that got his name in the book. His theorem states that so there has to be three conditions that are met before he actually says this works. F has to be continuous over whatever interval we're looking at. F has to be differentiable on that open interval. F of A has to equal F of B. So when you plug the values in, they have to equal the exact same thing. And if that's the case, then there is a value where the derivative is 0 between those 2 points. There's like, yep, totally trust him. All right, here's what he's saying. So let's say this is my function. We're going to look at it from here to here. So that's A, and that's B. Okay? So, is it continuous over between A and B? Is the graph continuous between A and B? Yes. There's no holes or asymptotes or anything else. Could I derive, if I gave you the function, could you take the derivative between A and B? Yes. We could find the slope at all points between A and B, therefore it's a derivative. Is f of A and f of B the same value? So what that states is that there is a horizontal line that goes between those 2 points. Okay? So, yes, as close as Mr. Baker's going to write a horizontal line today. All right, so there's a horizontal line that goes between those 2 points. What he says is that as long as the function is constant between those 2 points, there has to be a point between those two that my derivative is 0. Which means there has to be a point between those two that what happens? What happens when my derivative is 0 in most cases? There's no, my slope is 0, so that is a horizontal line, right? And if it's continuous and going down to the same point, it's going to be either a local min or a local max. Okay? So what he's saying is if you take two values that are exactly the same, and my function between them is continuous, at some point between those two, I have to have a local max or a local min. So he's got his name on a theorem in a book because he said, oh, if I'm going across the graph at 2 points, hey, at some point I have to go back down to it.
That makes so much sense.
It's like, that's literally what his theorem is. He goes, oh, if I keep going up, at some point I have to come back down to get to where I was.
Well, no crap.
Okay, that's what he proved. That's what happened when it was alive to be in the 1600s, when you could come up with things that totally make sense now. You get your name in the book. And everybody after that point has to remember your name. All right, that's basically all he said. So the extension of that is technically at, if I take any 2 points, the slope between those two, I can find another slope between them that is going to be parallel to it. Okay? So I could take any 2 points on it. I could take the extension of it, which is really kind of nice. So if I take a point here and a point here. So there's that. At some point in this thing, there's a parallel line to that. And actually, that's be right about here. So the derivative of that point is the exact same as the derivative of the slope of that one. That's the extension of it. We use it more, again, to find mins and maxes, to find those peaks. Because the peaks are really what actually matters. The stuff that happens between it is less useful and less important than the peaks on both directions. Okay? Yeah, no. And I just told you that one. Yeah, I just literally told you this. It's called the mean value theorem. I was like, I knew there was a name for it. So the mean value theorem states exactly what I just stated, that at any 2 points, there's going to be the derivative between those is going to actually exist at some point. So. All right. Let's do one problem. All right. All right. So we want to find the. If we were to actually, I'm going to graph this one so I can show you this one because it's nice when you see a graph of this. So it's x to the third minus x. And we're looking at this one from 0 to 2. All right, so here is my graph. All right, so what it says is that there is a point. So we actually figured out the slope real quick. 3x. There we go. All right. So there is there's a point somewhere over here that's going to have the exact same slope as that one. Okay? Why would that be important? Why do you think that'd be useful? Remember, sometimes you have to think past normal day-to-day stuff when we're starting to talk about rocket science. If I'm looking to intercept something, and that's the path that it's taking. If I can fly parallel to it, I'll be able to intersect it at some point because it's going to curve. If I'm flying parallel to its normal curve, right? Because I can figure out, like, okay, I know it's doing it right now. If I'm flying parallel to it and I know it's curving, I'm going to be able to intersect it at some point to find those places. So it's like, if it's whatever point this happens to be, it actually ends up be somewhere down here. Once they find that line, it's like, okay, if I'm flying this line, or if it's flying this, and I'm flying here, that's the slope, I can actually intersect it. So you can start to see how some of this stuff can be useful going forward. Now, when they were doing it, they did it totally theoretically. They had no real use cases for a lot of stuff. Since then, we have started using this stuff. I also think this stuff right here, especially the mean value theorem, is used a lot of times in finance too. Figuring out how things are changing and looking at that, being able to parallel the course of something else that's changing. So finding that is important. So now let's find it. All right, so the function, or the mean value theorem formula, says it's f of b minus f of a equals f prime of c times b minus a. So I know A is 0. I know B is 2. I need to find out my derivative. So what's the derivative of that? 3x squared minus 1. So now I can plug in all my information. So, actually, I need to find f of B and f of A. So f of 0 is 0, and f of 2 is 6. Okay, so now we can plug our information in. So I have 6 minus 0 equals 3c squared minus 1 times 2 minus 0. So 6 equals 6c squared minus 2. So I've got 4 equals 6c squared. So I've got 2/3 equals c squared. So c equals plus or minus 2 over the square root of 3. So I've got 2 points, right? But if we looked at the graph, only 1 point would exist. So which one of those 2 am I going to use and why? Where does C have to be? C has to be between A and B. It's got to be the positive version of it. So when you're finding them, that last step has to exist. So you're just going to do that one. So that's the C value. Do they give me my equation? They do not. All right. Easy.